Welcome to this explainer. Today we're going to turn you into a mathematical code breaker by unlocking the secrets of linear congruences. Have you ever wanted to know the absolute core math that keeps the modern digital world safe? Well, grab a notebook, because today you're the student, and we're going to walk step by step through the fascinating number theory that makes it all possible.
Okay, let's dive right into our roadmap for today. We'll be covering Section 1, Secrets, Codes, and Math. 2, Understanding Linear Congruence. 3, the Euclidean algorithm. 4, mastering backward substitution. 5, real-world RSA cryptography. And finally, 6, join Robo For Education.
Section 1, Secrets, Codes, and Math.
So, have you ever actually stopped and wondered how your sensitive information, like your credit card number, travels across the web without being stolen? I mean, it's not magic, right? It's mathematics. And it relies entirely on the fact that some math problems are incredibly easy to do in one direction, but literally notoriously difficult to reverse unless you have the secret key.
It all starts by turning text into numbers. You see, computers don't read letters at all. They read digits. Whether it's basic ASCII encoding, where a simple word like hello becomes a giant string of digits, or even an ancient Caesar cipher that just shifts letters down the alphabet, the absolutely crucial first step to hiding a message is always converting those words into mathematical values.
The simplest form of this is just replacing letters with integers. If we assign A to 1, B to 2, and so on, turning a name like James into 10, 1, 13, 5, 19 is a total breeze. But, simply swapping letters for numbers isn't exactly secure. Pretty much anyone can guess that. We need to lock those numbers up tight.
Section 2, Understanding Linear Congruence.
To do that, we use modular arithmetic. Think of it like a clock that just wraps around. If it's 10 a.m. and we add 4 hours, we don't say it's 14 o'clock, we say it's 2 p.m., right? We are only interested in the remainder left over after division. Two numbers are congruent modulo m if they give you the exact same remainder when you divide them by that m.
Now, if this looks like a terrifying wall of numbers, don't panic. This equation, ax is congruent to b modulo n, simply asks us to find an integer x that makes both sides have the exact same remainder when divided by n. It's basically like an algebraic puzzle, just with a very specific wrapping rule. And this is a massive shift in how we think about math. Unlike regular algebra, where your x can be some messy decimal or a weird fraction, in number theory, we are hunting for specific, clean, integer keys to fit our lock. We are looking for whole numbers only. No fractions allowed.
Section 3, the all-Euclidean algorithm. Okay, so how do we find these integer keys? Well, Euclid discovered a long time ago that we can find the greatest common divisor of two numbers, and the integer coefficients needed to get there using a highly reliable, step-by-step algorithmic process. He proved that for two numbers p and q, there are integers a and b such that ap plus bq equals their greatest common divisor.
We can think of this forward Euclidean algorithm as walking step by step into a mathematical maze. Say we start with two numbers, 329 and 271. We divide the larger by the smaller, find the remainder, and then repeat the process with the previous divisor and that new remainder. We just keep stepping down, down, down until we hit a remainder of 1.
Section 4, Mastering Backward Substitution.
Now for the fun part. Here is where we learn backward substitution to get out of the maze. Let's take this one step at a time, remembering our basic algebra rules. The absolute golden rule for this tutorial. You have to treat your remainders like variables, like an x or a y, and keep them isolated in brackets. Resist the urge to multiply them out, or you will completely lose your way.
We start our journey backward by writing our final remainder, which is 1, in terms of the numbers from the step right before it. So looking at our previous steps, 1 equals 39 minus 2 times 19.
Next, we look up one more step in our forward maze. We saw earlier that 19 was equal to 58 minus 1 times 39, so we carefully substitute that whole expression in place of the 19, and notice how we keep the new numbers safely wrapped up in those brackets.
Now we use our algebra skills. We distribute that -2 and combine the 39 terms together. Remember, treat the 39 and 58 like variables. We don't actually multiply 3 times 39 here. We just say we have 3 39s minus 2 58s. We are slowly, carefully building our way back to our original huge numbers.
By repeating this careful substitution all the way up to the steps of our forward algorithm, we eventually get right back to our starting numbers, 329 and 271. And look at what's sitting right next to them. We found our secret integer coefficients, -14 and 17. Boom!
You're doing absolutely great with this. And honestly, the best part is that today, you don't have to do this by hand for huge numbers. Modern computers use this exact same backward substitution logic we just learned to handle massive, multi-digit numbers for us in mere fractions of a second.
Section 5. Real-world RSA cryptography. So why does finding these integer values even matter? Well, let's connect these steps to real-world cryptography, specifically RSA encoding. In RSA, we use public keys based on giant prime numbers to lock a message. Imagine Alice wants to send Ben a secret message, like the letter M, which translates to the number 13. She encrypts it using a public key, scrambling that 13 into a secret code of 602.
Now, anyone eavesdropping can see the 602, but it's meaningless garbage to them. The only way Ben can decrypt that message and get the 13 back is by finding the secret decoding key, which mathematicians call D. And how does his computer calculate D? By using the exact Euclidean algorithm and backward substitution process we just walked through. By solving that linear congruence equation, the secret integer key is revealed.
Section 6. Join Robo for Education. Knowing how these locks work really makes you realize just how incredibly valuable giant prime numbers are. Because if someone can factor the giant numbers used in these public keys, they can run the backward substitution themselves and break the code. That is exactly why there are literally cash bounties out there, sometimes $50,000, just for factoring massive 200-digit prime numbers. The math is simple, but the sheer scale of it is staggering.
I really hope you enjoyed this deep dive into number theory. To keep mastering the math behind the modern world, make sure you subscribe to the Robo For Education YouTube channel. Be sure to follow our site, our blog, and our social accounts, and definitely join our community at RoboPlace at Google Chat. I'll leave you with this final thought. If the math is so beautifully simple, but the giant scale is the only thing keeping your bank account safe, how long until quantum computers make those $50,000 bounties look like child's play? Keep learning, keep calculating, and I'll see you in the next explainer.